Hello class, my name is Martin Sanchez and my project topic is securing mobile ad hoc networks. So I will be presenting my project research progress today. I will briefly introduce MANETs, their security challenges, what a secure protocol should do, and the solutions I have found in research. First of all, I would like to quickly recap the key characteristics of a mobile ad hoc network. MANETs are a group of self-organized, self-configured wireless networks without the need of infrastructure. Contrary to an infrastructured wireless network, in these networks, all the devices act as both a node and a router. MANET is formed based on the collaboration between independent peer-to-peer nodes to communicate with other nodes for a particular application. No prior base station or organization is defined, and all devices have the same role in the network. Additionally, there are no preset roles such as routers or gateways. Each device can work as a node and a router at the same time. This allows for highly dynamic topologies, and this means that the nodes are free to move around, so they could be in and out of the network, constantly changing their links and their topology. In addition, the links between nodes could be bidirectional or unidirectional, and this feature, however, causes high user density and large level of user mobility. Wireless links that connect the MANET nodes have much smaller bandwidth than those with wires. Due to the effects of multiple accesses, multipath fading, noise, congestion, fluctuation, and signal interference, the capacity of a wireless link can be degraded over time, and the effective throughput may be less than the radio's maximum transmission capacity. MANET devices are also energy constrained because most of them are small portable devices that are dependent on a battery for power. Therefore, it is important to have energy efficiency as an important parameter when developing or evaluating routing protocols for MANETs. And lastly, wireless links made MANET more susceptible to physical layer attackers such as eavesdropping, jamming, spoofing, and denial of service attacks. Here, all the networking functions like routing, packet forwarding are performed by the nodes themselves, and because of this reason, securing a mobile wireless network is very challenging. The increased possibility of eavesdropping, spoofing, and minimization of denial of service type attacks should be carefully into consideration. The distributed nature of operational security, routing, and host configuration causes to the absence of centralized firewall here. Since devices are both nodes and routers, this network topology eliminates the need of infrastructure to create a network, which creates great advantages for certain applications such as environmental monitoring, healthcare, military, surveillance, location tracking, disaster recovery, and many more. However, no infrastructure also creates a number of challenges in the security area, which is a crucial shortcoming for the intended applications such as in the military, for having a breach in the network could not only render the application useless, but instead turn it into a hazard and a way in for enemies to gather sensitive information. Because of their unique characteristics regarding open network architecture, shared wireless medium, stringent resource constraints, and highly dynamic network topology, MANETs have specific security challenges. Consequently, the existing security solutions for wired networks do not directly apply to the MANET domain, so we can't really use the security protocols that have already been established for wired networks and apply them to MANETs. One distinguishing characteristic of MANETs from the security design perspective is the lack of a clear line of defense. Unlike wired networks that have dedicated routers, each mobile node in an ad hoc network may function as a router and forward packets for other peer nodes. The wireless channel is accessible to both legitimate network users and malicious attackers. The existing ad hoc routing protocols, such as ad hoc on-demand distance vector or AODP and dynamic resource routing or DSR, and wireless MAC protocols such as 802.11 typically assume a trusted and cooperative environment, and as a result, a malicious attacker can readily become a router and disrupt network operations by intentionally disobeying the protocol specifications. And security never comes for free. This is especially relevant in MANETs, where most of its devices have resource constraints requiring bandwidth, computation, and power. When more security features are introduced into the network, in parallel with the enhanced security strength is the ever-increasing computation, communication, and management overhead. Consequently, network performance in terms of scalability, service availability, robustness, and so on of the security solutions becomes an important concern in a resource-constrained ad hoc network. While many contemporary proposals focus on the security vigor of their solutions from the cryptographic standpoint, they leave the network performance aspect largely unaddressed. In fact, both dimensions of security strength and network performance are equally important, and achieving a good trade-off between the two extremes is one fundamental challenge in security design for MANETs. Before going over the current proposed solutions to these challenges, I think it is important to define what a secure protocol should be and what it should deliver. The ultimate goal of the security solutions for MANETs is to provide security services, such as access control, authentication, non-repudiation, confidentiality, communication security, integrity, anonymity or privacy, and availability to mobile devices. Access control is needed to ensure that malicious nodes are kept out of the network. Authentication is the process performed by two entities to identify each other. In the context of MANETs, this is to prevent an unauthorized node to utilize the network's resources and potentially attack it. There's two approaches to authentication: direct and indirect. In direct authentication, nodes use pre-shared symmetric or asymmetric keys for verification, and in indirect, a third party is responsible for the verification. Non-repudiation prevents nodes from broadcasting false information about previous transmissions, mitigating replay and related attacks. Confidentiality refers to the prevention of information being compromised by unauthorized agents. Encryption is often used to provide confidentiality of information by data encoding. Communication security ensures that information only flows between source and destination without being diverted or intercepted. Integrity refers to the protection of information from unauthorized alteration. Integrity measures should provide assurance in the accuracy and completeness of data. There are many countermeasures that can be put in place to protect integrity. Hash verifications and digital signatures can help ensure that transactions are authentic and that files have not been modified or corrupted. Anonymity in a MANET context refers to the protection of the privacy of the nodes and routes. Anonymity should be one important part of the overall solution for truly secure mobile ad hoc networks, especially in certain privacy vital environments. For example, in a battlefield, we not only want to ensure that adversaries cannot disclose the contents of our communications, meaning confidentiality, or disable the communications, meaning availability and integrity, but we also expect that the identities and location information of parties in communications are anonymous to adversaries. Otherwise, enemies may deduce important information about the location or mobility model of communication parties, which can be used to locate the target of their physical attacks at a later time. In order for an information system to be useful, it must be available to authorized users. So availability measures protect timely and uninterrupted access to the system. Some of the most fundamental threats to availability are non-malicious in nature and include hardware failures, unscaled software downtime, and network bandwidth issues. but malicious attacks include various forms of sabotage intended to cause harm to an organization by denying nodes access to the network. Today, I will go over 5 proposed solutions that I've reviewed from the literature on this topic. These are secure data transfer using symmetric and asymmetric cryptography, FAES AOMDB, modified AODB against black hole attacks, Superman, and secure and energy-efficient stochastic multipath routing. One of the solutions I'm going to talk about today is the secure data transfer using symmetric and asymmetric cryptography by Kapoor and Khatri from the Amity Institute of Telecom Engineering and Management. There is a need to secure the data transmission against passive attacks such as eavesdropping, traffic analysis and monitoring, and active attacks such as modification and replay of data packets. The proposed technique by Kapoor and Khatri attempts to overcome the attacks on data payload by employing cryptographic techniques. It assumes that a link between the source and the destination has been established using the routing protocol at the network layer. A session key for the symmetric cryptographic algorithm is exchanged by using the public key of the destination. A source hash of the input data is computed and the private key of the source is used to generate the digital signature of the input data. The plain data is then encrypted using the symmetric cryptographic technique and the session key. The encrypted data along with the digital signature of the plain text are transmitted to the destination, and at the destination the hash is extracted from the received digital signature using the public key of the source. The encrypted received data is decrypted using the session key, and the calculated hash of the received plain data is calculated and is compared with the received hash. If the received hash and the calculated hash of the received text match, then the received data is accepted, and if not, it's rejected at the destination. This technique uses a symmetric cryptographic algorithm to encrypt the data and achieve the confidentiality requirement of a secure protocol. Hashing ensures integrity of the data because any change to the data will change the hash value, detecting any malicious attempt to modify or corrupt it. And the digital signature takes care of the authenticity requirement because any change of the data will also change the signature. One thing to note, though, about this proposal is that it works at the application layer, so it doesn't create overhead at the network layer. Furthermore, if the routing protocol is insecure, this can compensate for it. However, symmetric and asymmetric encryption requires high computational resources, which in mobile devices can result in latency, but most importantly, it can result in higher power consumption. This is a critical area that the paper does not even consider. And while having an extra level of security at the application layer seems like a good idea for redundancy, I believe it would be necessary to evaluate the trade-off between the extra security and the power consumption. Another area that could be explored is to use a not secure but efficient routing protocol and utilize this technique, but this may not be good enough for certain applications, so it may be an area to further explore. Another interesting technique is the false AES-based AOMDB protocol. Before going into the details of this protocol, I think it is necessary to explain the protocols on which it builds on. This technique takes the OMDB protocol as a base and aims to make it more reliable and secure to black hole attacks. The ad hoc on-demand multipath distance vector routing protocol, or AOMDB, is a routing protocol used to discover multiple active paths between the sender node and the destination node. The AOMDB protocol itself is based on the AODB protocol, which is a reactive routing protocol, so it establishes paths on demand. As we can see from the diagram, if node S wants to direct a data packet to node B, node S starts a discovery of route by disseminating a routing request message, which is received through S direct neighbors, the S direct neighbor C, and the message is rebroadcast by this node to establish the route. Since C has a direct path to node D, it sends back a route reply as a unicast to node S. In AOMDP protocols, this is the same process, but multiple routes are found between the source and the destination, so in case of a route failure, it can use alternate routes to deliver the packet. So AOMDP builds on top of AODP, but offers better performance for control overhead of the network and packet delivery ratio. In turn, the FAES AOMDP utilizes the AOMDP routing protocol as a base, but enhances security and reliability by FAES encryption algorithm to encrypt data packets during transmission. Additionally, power consumption is taken into consideration by using EBR algorithm to calculate the energy contribution of each node. Before explaining the proposed technique in more detail, I would like to go over the concept of a black hole attack. In this type of attack, the malicious nodes reside in the network and portray that they have the shortest path for the destination. This makes the malicious node to enter in the network, and when the source node starts sending packets, it just drops and destroys them. So if we look at the diagram, in this case we have two paths from source to destination, but the shortest path, which is the one at the top, contains a malicious node that replies to the source saying it has the shortest path. So when it receives the packet from the source, which is going to pick that path because it's the shortest one in theory, the malicious node does not pass the data packet along in the network, but instead it drops it. As I mentioned before, in the FAES AOMDP algorithm, the source node broadcasts a route request to identify neighbor nodes within range, and it is repeated until the message reaches the destination and the replies reach the source with the available routes from source to destination. Then, the energy contribution of each node is calculated using EBR algorithm, and in this case, before sending the data packets, they are encrypted using FAES, and this is the main difference between this proposed technique and AOMDP. By encrypting the data packets at this point, they are being protected from malicious nodes and black hole attacks. Lastly, the routes are sorted using KNN algorithm with minimum distance to select the shortest route. The encrypted data is transmitted through the selected shortest route that does not exceed an energy consumption threshold, and it is decrypted at the destination using FAES decryption. So, to follow the flowchart, first the source node broadcasts a route request message within the network to discover the routes and destination for the data transmission. If the node is not equal to the destination, it simply forwards it to its neighbor nodes until the route request reaches the destination. When the destination node receives the route request message, it sends a route reply message with its routing information through the intermediate nodes to the source. The source receives this route reply of destination, and it updates its routing table with the routing information of the destination and intermediate nodes. Then the energy contribution of each node is calculated using EBR algorithm to determine the energy consumption of each route. If routes are established, source counts on routes with the minimum energy consumption to route the data packets. The FAES encryption algorithm is used to perform encryption of data packets before the transmission, and the KNN algorithm is used to select the shortest route for the data packets delivery. The shortest route is sorted out using this KNN algorithm, and packets are delivered with the selected shortest path to the destination. The encrypted data packets are routed through the shortest path or the path with minimum hop counts and energy consumption. And the data packets are finally decrypted using FAES decryption algorithm at the destination. And the reason why FAES works against black hole attacks is because in each encryption round, a false round key is added to decrease the association between the actual key and profile of power consumption. Since throughout the encryption process, it is hard for an attacker to find the correct encryption key as it is masked with the false round key. And the results of these paper simulations and tests concluded that this scheme offers higher throughput along with lower energy consumption, which is considered to be good features for the emergency-based applications of MANETs. Furthermore, the rate of success of this proposed scheme to guarantee and ensure the packet delivery to the destination is very high through multiple paths and in a more secured manner. There is another MANET routing technique aimed at securing communication against black hole attacks that is also based on AODP. As I've explained in previous slides, the main objective of a black hole attack is to make the destination node unreachable or to downgrade the communication throughout the network. In this scheme, a baiting technique was developed that depends on the own node ID. The detection of a black hole node starts by broadcasting a bait request to all adjacent nodes. The bait request contains a source sequence number and source ID. When the source node receives it, it checks that if there is a reply that has a higher DSN than its own SSN. This indicates that the reply came from a black hole node, since there is no node in the network that should have a higher DSN than SSN of the source node. After the detection of the black hole node in the network, the source node broadcasts a black hole alarm to all adjacent nodes to notify them. So if we look at the diagram, the algorithm works like this. The source node broadcasts the fake route request packet with its own source sequence number and address in the destination sequence number and destination address. When the legitimate nodes receive this fake route request packet, they will compare the source sequence number in the fake route request it received with the sequence number of the source described in the table. As the source node sends its own sequence number, it will be more obvious that it will be the latest or the fresh one. The intermediate node will have the source sequence less than the described in the fake route request packet, so it will not reply with a route reply packet. But if there is a black hole node in the network, then it will reply with the route reply packet and advertise itself as having the shortest path with highest source sequence number, which this should be impossible because it can have a shortest path to the source, from source to source. So the source node will then detect the black hole exists in the network, and it will send the alarm packet having the list of black hole nodes to the rest of the nodes. This seems like a pretty simple and smart way to detect a black hole with little overhead, but there are limitations to this technique. Even though we've seen that this is a much simpler approach than the FAES AOMDP. And the limitations are that a smart black hole node can check if the received route request asks for a route to the same source of the route request, and then it simply can choose not to reply, which would make the solution useless. But even worse, a smart black hole node can use the black hole alarm and start broadcasting false black hole alarms to isolate selected nodes in the network. So not only can this solution be useless, but it can actually be harmful. There's another MANET protocol addressing security, and fortunately this one has an easier name to pronounce. It's called Superman, which stands for Security Using Pre-Existing Routing for Mobile Ad-Hoc Networks. The protocol is designed to address node authentication, network access control, and secure communication for MANETs using existing routing protocols. Superman combines routing and communication security at the network layer. This contrasts with existing approaches, which provide only routing or communication security, requiring multiple protocols to protect the network. So far, I've talked extensively about black hole attacks, but there are many other types of attacks. We can divide these types of attacks into 5 categories. Destruction, which involves completely removing a packet from the network and deleting it locally, preventing it from reaching the destination and destroying the packet. Corruption and modification, which involves making a packet unreadable or changing the content of the packet. Then theft, loss, or removal refers to stealing packets from the network for further analysis, causing packets to drop or removing them from the network. Disclosure, which is revealing network information by rebroadcasting received packets to untrusted nodes. And then there's interruption of services, which is a disruption of any service that the network offers. And this results in loss of service or unacceptable completion time. The approach taken by Superman is to allow existing network and routing protocols to perform their functions whilst providing node authentication, meaning access control and communication security mechanisms. And the reason behind this is that access control could be the security dimension that might address the issue of implicit trust within a MANET. By closing the network to outsiders, the issue of assumed cooperation is circumvented. Closing the network requires a means of allowing the nodes to join and leave the closed network, and authentication provides a means by which a node may be identified as trustworthy. By using a certificate to confirm that they share a trusted authority, two nodes may authenticate one another based on their shared trusted authority. So, Superman implements a virtual closed network architecture to protect both network and application data, and it operates at the network layer of the OSI model, and it is designed to provide a fully secured communication framework for MANETs without requiring modification of the routing protocol. Here I will go over the certification process of the Superman protocol. First, each node is provided with a certificate from a trusted authority in order for it to join the Superman networks. And the joining node, in this case node A, seeks to join a network by periodically broadcasting a discovery request, which contains its public key share. This continues until it receives a certificate request from a networkable node, in this case node B. And having received a discovery request from node A, node B sends a certificate request packet containing its public key share to A. Then both nodes perform Diffie-Hellman key exchange using the shared public keys they now hold to generate end-to-end and point-to-point symmetric keys, which are used to encrypt and provide integrity to the rest of the access control process. Upon receiving a certificate request from B, A sends a certificate in a certificate exchange packet to B. Then B checks the integrity and authenticity of this packet using the shared symmetric point-to-point key. Then B also checks the certificate's authority against the trusted authority hierarchy of its own certificate, and the certificate contains the public key shared previously by A. And if the certificate is deemed authentic, A is added to B's security table. And if this certificate fails, the key credentials generated for node A by B are dropped and the process ends. If it doesn't end and the certification is successful, B responds to A certificate exchange packet with its own certificate exchange with broadcast the key. And A repeats what B just did, checking the authenticity of the certificate. If A has a broadcast key, it transmits a broadcast key exchange packet containing the new key, which is secured with the original key before committing the new key to the security table. B broadcasts an SK invalidation packet invalidating any previous credentials A may have had with nodes within the network, and this is to prevent the accumulation of expired security data on nodes that may be isolated from previous invalidation events. Following this method, it is possible for a node to build up a collection of symmetric keys representing its links with every other node it has exchanged security details with. So, Superman addresses the 8 security dimensions that we detailed at the beginning of the presentation by providing a closed MANET with end-to-end and point-to-point security features. Access control is provided by Superman's network joining method. Authentication is provided by certificates, which allow the relationship between the node and the trusted authority to be confirmed. Non-repudiation is provided by timestamps in each Superman packet header. Confidentiality is provided end-to-end by payload encryption using AEAD. Communication security is maintained by encrypting and performing source authentication end-to-end and checking authenticity and integrity at each hop. Integrity checking is provided by using a tag for packet integrity. Availability is maintained using each node security table, which stores valid authentication credentials. And privacy is provided by end-to-end encryption with keys that are specific to the link between two nodes or a node and the network. The last protocol I want to mention is the secure and energy-efficient stochastic multipath routing protocol. This technique computes multiple paths between source and destination and selects an energy-efficient path stochastically. The objective of this protocol is to achieve both secure and energy-efficient routing for MANETs, which, as I mentioned earlier, are two areas that need massive improvement in mobile ad hoc networks. The authors of this technique reject the use of cryptography to secure information in a MANET due to the high computational resources taken by encryption algorithms, which can create both lag and battery depletion in a MANET environment. Instead, they propose to secure data flow by forwarding packets through random paths from source to destination so that it is difficult for attackers to jam, intercept, and hijack data, as they would need to listen to all possible paths in order to do so. In MANETs, the route discovery phase may create multiple paths between source and destination, where one or more paths may be the shortest, but it is not necessary that the shortest path is always energy efficient. In this scheme, the route discovery phase creates all possible node disjoint paths from source node to destination node. Once these paths are created during the route discovery phase, a source node selects one such path during each time slot for transferring data between the two nodes. This protocol generates multiple paths between source and destination, very much like the AOMDP protocol that we reviewed a few slides ago. But in this technique, there's an extra piece of information in the route request packet, which is the minimum energy factor. Whenever an intermediate node receives the first route request packet, it compares the minimum energy factor of the node with the threshold of the energy factor defined by the trust module. The destination node receives multiple route request packets with different hop counts. To limit the number of hop counts of the received route request packets, the destination node computes a threshold value of hop counts. Based on this threshold value, the destination node discards few route request packets. And the source node randomly chooses a path in each time slot from the multiple paths according to the optimal value. So, from the attacker's point of view, it will be very difficult to jam, intercept, and hijack the data flow in any state of the routing stage. Additionally, the proposed stochastic multipath routing process distributes data flow by using alternative paths among multiple paths in each time slot in the routing stages. So, it spreads the energy dissipation among the nodes in the network. As a result, a uniform energy consumption environment is ensured by the proposed routing scheme. And this is very important because in MANET, we need to take into consideration the energy, the depletion of the batteries, because that was keeping the nodes alive. But not only that we use less battery in an efficient protocol, but also that the energy load is distributed uniformly, and this is what this protocol achieves. And these are all the routing protocols I wanted to discuss today. So with that, these are my references, and I wanted to thank you all for listening to my presentation.